Let's continue our discussion on heat and heat transfer, specifically expanding into calorimetry. And I apologize for the horrendous quality of this joke. So in terms of temperature, just as a review, temperature is proportional to the average molecular translational kinetic energy of your substance. The internal energy, U, is the total molecular kinetic and potential energy combined. Whereas the heat, specifically, is the molecular energy that's transferred from a high to a low temperature, so down a gradient. So as an example, if we take a red hot piece of iron, here represented by this red blob, and we drop it into a bucket of cold water, the water will heat up. So the internal energy of the water in this particular scenario will increase, but the internal energy of the iron will decrease. The energy will flow from the metal into the water. And we can actually quantify this by talking about the specific heat capacity of any material. So any material will have a specific heat capacity, and that's the heat that's required to raise the temperature of 1 gram of a substance by 1 degree C or 1 Kelvin. Remember, these units are synonymous in terms of a temperature change. So the unit here is joules per gram degree C. Now, you must be a little bit careful here in that sometimes you can see this given in terms of the kilogram, and the examples in the slide set deliberately go through that change. But you must be careful because C is what's known as the specific heat capacity. So the specific heat capacity is combined into this equation. Q, which is the heat transferred into the system, is equal to m, which is our mass. In this case, we're leaving it in grams. C is this specific heat capacity value, and delta T is our change in temperature. So delta T is take your final temperature and subtract your initial temperature. Now, C is where you have to be a little bit careful. This value of C can be given in joules per gram Kelvin, joules per gram degree C, or it can be given in joules per kilogram Kelvin. And you have to make sure you're using the right version of C. And C, being the specific heat capacity of the material, is often a value you can look up in a handy table. These have been experimentally determined for most materials. So C, the specific heat capacity, is the heat needed to change the temperature of a unit amount of the substance. So if we rearrange the previous equation, C is essentially Q over the mass times the temperature change. C is Q over m delta T. And that'll give you units of joules per kilogram Kelvin, or joules, perhaps even mole Kelvin, or joules per gram Kelvin. So be careful that you're using the right value of C if you were to look one up. Rearranging this equation again, we can of course get the temperature change if we know the heat energy that's input to the system. So here, delta T is Q over mc. So let's take a look at an example. What amount of heat here is required to raise the temperature of 100 milliliters of water from 45.6 Celsius to 52.8 Celsius? Well, in this particular case, you're given a volume of water. This is not a mass and could not be substituted in for m. So you have to figure out what the mass of the water is to substitute into our equation. Delta T is a fairly simple matter of subtracting these numbers. If we're to do this, then we need to look up C for H2O. So we would look to a table for the specific heat of water and find that it's 4.184 joules per gram here, degrees Celsius. So we're going to work in the grams regime for this particular problem. The density of water is 1 gram per milliliter, which turns out to be quite fortuitous. So 100 milliliters basically equals 100 grams, a one-to-one conversion here. Let's apply Q equals mc delta T. C was a value we looked up from a table that I gave you in the previous slide. Multiply that by 100, multiply that by our temperature change, 52.8 minus 45.6, will give us a Q of 3012.48 joules. So here we've worked in joules, and this is the unit I would prefer people work in general, maybe the kilojoule if we're looking at very large numbers. But in terms of the units, here we're looking at joules. You can also see some others, such as calories. And calorie, this is the typical one you see when people are dieting, counting calories, things like that. And if you pick up any food packaging, you will typically see the amount of energy contained within that food quoted in calories. And calorie, if we're looking at the definition, is the heat needed to raise 1 gram of water by 1 degree Celsius or 1 Kelvin. And it's equal to 4.186 or about 4.2 joules. Now, the British thermal unit, which I would add I have hardly ever encountered in Britain, is usually the kind of unit you see when people are doing such things as buying water heaters. And the British thermal unit, or BTU, is the heat needed to raise 1 pound of water by 1 degree Fahrenheit. And that's equal to 1054.35 joules. So if we're talking about heat capacities of things, here's some typical values for things like water, which is ubiquitous in most materials that we eat or drink or whatever. So that's about 4,185.5. Notice the change from the previous example because this is a specific heat capacity quoted in joules per kilogram Kelvin or joules per kilogram degree C. So it's increased by 1,000 here. Copper, 376.8, iron, 460, just to give you ideas of specific heats, which are often, as I say, tabulated. So if you find yourself doing a question with Q equals mc delta T and find that you don't have enough information, it may be because you're intended to look up the value of C. And as I said, different units exist for energy. If we're in the USA here, we can look at the back of a food container, here a can, and you can see the energy content listed in calories and also in kilojoules in this case. Most countries use joules or kilojoules, and the USA still uses calories. Either one is fine as far as it goes, but just be aware of this change. And if you go to the international food aisle of a local supermarket, you'll find a label slapped crudely over the values in joules, giving you the values of the energy content of these foods in calories. You can tear it off and take a look for yourself. So let's look at a particularly florid example, here ripped from the TV. So here is Rick about to fire at this zombie and misses the zombie and puts his bullet into a pine fence. The bullet weighs 2 grams, has a velocity of 200 meters per second, and you're given the specific heat of lead here in kilograms per Kelvin of 125.6. The question we have is what is the temperature change of this bullet? So he fires the bullet with a specific energy. It's going to hit this fence and then transfer thermal energy to the fence. So let's write down what we have. We have the bullet mass, we have the velocity, and we have the specific heat of lead. What is the temperature change of the bullet? Now we don't know a lot here about temperatures and energies. What we do know is that the bullet has a speed, a velocity of 200 meters per second. That relates to the kinetic energy of the bullet. If you cast your mind back to mechanics, kinetic energy is 1/2 mv squared. We have m, we have v. So let's make an assumption here. Not quite right, because when this bullet hits the fence, there will be sound, there will be mechanical fracturing, etc., etc. But we're not going to account for that now. We just want to get an idea of how much the temperature may increase. of this fence. So we're going to say that all the kinetic energy of this bullet goes into thermal energy. That means half mv squared, the kinetic energy of the bullet, is equal to 1/2 2 times 10 to the minus 3 kilograms here, because this is 2 grams and we want to put this into kilograms, times 200 squared. This is the velocity of the bullet. This will give us 40 joules, which we're going to set equal to the Q, the heat energy of the system. Now, as we used before, we also now know Q is equal to mc delta T. We've set Q equal to 40. We have the value of C right here in joules per kilogram Kelvin, hence we used kilograms here. So we're nicely in joules. And we can rearrange for delta T. So delta T is Q over mc. Here's our Q value. Here's our m, our mass in grams of 2 times 10 to the minus 3 kilograms times 125.6 kilogram Kelvin. This will give us a delta T of 159 Kelvin or 159 Celsius. Let's take a look at one more example. Here we've got 79.3 joules of heat, and we're adding it to a 111 gram piece of aluminium because there's an I in it, at 22.5 degrees Celsius. Apologies for the degree missing here. So this is in grams, so we have to be a little careful. What's the final temperature of this metal when the C, the specific heat of the aluminium, is 900 joules per kilogram Kelvin? Well, Q is equal to mc delta T. We want to find out what the final temperature is. That means our final temperature of T is going to be the initial temperature plus whatever temperature change we get, which is Q over mc. That means substituting in, we have our 22.5 here, that the temperature of the metal already was at, plus 79.3 over 0.11, so this is 111 grams now converted to kilograms, times 900 joules per kilogram Kelvin. That will give us 23.3 degrees Celsius. So we've already discussed phase changes, and we discussed them briefly in terms of heat of vaporization, heat of fusion, but now we've discussed such things as calorimetry and heat budget and how we can calculate these values. We can return to this, better armed to solve problems. So as we said before, phase changes depend on the potential energy that's supplied to our system to make it transition from a solid to a liquid to a gas. And during our phase change, the potential energy, not the kinetic energy, is what's responsible for this change in phase. So the kinetic energy, remember, is what we call temperature. So during the transition from solid to liquid and liquid to gas, we're increasing the potential energy and the overall heat energy and not the temperature. So heating or cooling a changing phase doesn't change its temperature. So when we melt, boil, freeze, condense, we're adding or removing heat and changing the potential energy, not the kinetic energy of our substance. And as usual, water freezes at 0 Celsius, boils at 100. So not all heat transfer can be expressed as a direct temperature change, or delta T. So some of this is a recap. And as we saw in previous slide sets, we have temperature here, and here's our ice melting, our water boiling, and here's our energy or heat input here in joules per kilogram. So our temperature increases as we start moving the ice around, as the ice molecules shift around thermally. Our ice melts, gains potential energy, liquid water ends up with kinetic energy of the molecules changing, and then we have another plateau in temperature here at 100 as the potential energy is increased to change this liquid water into gaseous water and steam. And that created two specific values. So the potential energy of our phase change is the energy required to change the phase of 1 kilogram of a substance. That means we defined previously water's latent heat of fusion, its melting energy, 335,000 joules per kilogram, and its much higher latent heat of vaporization, the energy required to actually vaporize and create steam. So this was 2,255,000 joules per kilogram. And these are referred to as the latent heat of fusion, LF, and the latent heat of vaporization, LV. Don't mix these two up, that's kind of critical. So the heat of fusion is the heat required to change 1 kilogram of material from a solid to a liquid. The heat of vaporization, LV, is the heat required to change 1 kilogram of material from liquid to vapor. And we often use water as our typical example. Here's our melting point at 0 Celsius, here's our boiling point at 100, and the accompanying heats of fusion here in kilojoules here, so those thousands are taken off because it's in kilojoules per kilogram and kilocalories per kilogram. So these are presented this way, so this table is not huge. We can actually define these heats of fusion and subsequently the heats of vaporization for a lot of different materials. Gases, oxygen, nitrogen, even at standard temperatures and pressures, these things will often just be in its gaseous form anyway. So here's the boiling point at negative 183 Celsius. Compare that to the boiling point of water at 100. Nitrogen the same. Alcohol vaporizes very easily, which is why it burns so well. Water, of course, lead, silver. We can define these things for solids. We can vaporize any of these things if we wish. So say the vaporization here, temperature of iron is 1,500, the vaporization energy is 1,520 kilocalories per kilogram or 6,340 kilojoules per kilogram, or it has a melting point of 1538 Celsius or a boiling point of 3023 Celsius. So if you were in the vicinity of boiling iron, you would probably not be alive for very long. So those are sort of typical values that you should expect to see in terms of latent heats. And latent heat is very useful. And the reason I point this out is that sometimes you can just skip doing the whole Q equals mc delta T if you are provided with specific values, such as the mass and the fact that this is, say, vaporizing at the vaporization point or at the point of melting or freezing. So we can say Q equals ml, and this can be LF or LV, the heat of vaporization or heat of fusion. So when you're looking at what we call calorimetry, this is the science of figuring out how much energy is in a particular material. It's actually a technique in trying to figure out how much energy is in, say, a piece of food, how much energy was contained in melting ice, how much energy was contained in the iron that we dropped into the water. And we can do this by calculating how much heat has flowed into or out of a system. So what we often assume is that we have an isolated system, nicely insulated to the surroundings, and then we can want to account for all the energy transfer sources. We then apply conservation of energy, and if we don't have a phase change occur, we can use mc delta T. So you can still use Q equals mc delta T in place of L, but if you have a phase change from a solid to a liquid or a liquid to a gas, you can look up L and make your life a bit quicker and easier by doing Q equals ml instead of Q equals mc delta T. So the latent heat of vaporization, LV, as we said, is relevant for evaporation as well as boiling. So heat added during a state change, that's to go from, say, a solid to a liquid, does not increase the kinetic energy of the individual molecules. So this LV is really accounting for that potential energy that's going into the system, that's breaking the bonds so the next phase can occur. And that's where you can use your heat of fusion or heat of vaporization to find these values. And these tend to get given as L, or sometimes you can see these in terms of a H. It really depends how they're expressed. I'm showing you the alternate notation just in case you see HV instead of LV. But essentially this is exactly the same formula. This could be HF, this could be HV, it could be LV, LF, and the unit here of our heat of vaporization of our latent heat is joules per kilogram. So here's a nice one. 115 gram sample of liquid is boiled over 10 minutes. As the liquid boils, the temperature remains constant and 2.27 times 10 to the 5 joules of heat are absorbed. After 10 minutes, all the liquid is boiled away. What was the heat of vaporization of the liquid? So here's all our information. As always, write out what you have. We're going to say Q is 2.27 times 10 to the 5 joules. That is all of the heat that's been absorbed. That's given in the question. You just need to interpret that and say heat is absorbed. This is Q. After 10 minutes, all liquid is boiled away. It doesn't really matter if it took 10 minutes, 3 hours, 3 minutes, or 20 seconds for this heat to be absorbed. It's irrelevant to this particular problem. What was the heat of vaporization of the liquid? Well, we've converted our mass here, which is always a good idea unless you're trying to equal up to some kind of constant given in a different value, given in different units even. So our 115 grams here is converted to kilograms and gives us 0.115 kilograms. Q, as we said before, is equal to M times HV or LV, doesn't matter. Substitute in, rearrange, and we will find the heat of vaporization for this particular liquid of 1.97 times 10 to the 6 joules per kilogram. So that's the heat of vaporization. Again, heat of fusion, same equation. Q is equal to M times the heat of fusion. And that's the heat required to change the amount of a solid, some amount of a solid to a liquid at a constant temperature. So the heat of fusion of ice at 0 Celsius is 3.4 times 10 to the 2 joules per gram here. How much heat is needed to change 75 grams of ice at 0 Celsius to liquid water? Well, HF here is 3.4 times 10 to the 2 joules per gram. Mass is 75 grams. We know Q is equal to M times HF. Substitute our values in. Everything's in grams in this particular case, so I'm mixing up the units deliberately, even though I'd prefer you use kilograms where you can. And Q will be 2.55 times 10 to the 4 joules, which is about 2.6 times 10 to the 4 joules. And this is also a good example of rounding. If you want to round on an exam or on an assignment or something like that, especially when you're looking at multiple choice assignments, say you're looking at multiple choice and you calculate 2.55 times 10 to the 4 joules, but 2.6 times 10 to the 4 joules is one of the only quoted answers, you can of course go to the nearest rounded answer if it's reasonably rounded. Rounding this to 3 times 10 to the 4 would of course be a little bit brutal. So in some cases, if you're using multiple materials or multiple energy sources, you can calculate Q total and add up MC delta T for all sorts of different materials, especially when you're looking at calorimetry and you're dropping, say, metal into water. You could do equals Q equals MC delta T and equate that to Q equals M times LF or LV for your fluid. And you'll often see this kind of thing done in a lab. And this is what we mean by something like calorimetry. Here we have an insulating jacket, quite often some form of styrofoam, and then inside we have a glass beaker with water. You can put a thermometer into this, and then you can either drop a material in containing thermal energy, or you can stir this and provide thermal energy through agitation of the liquid, through stirring it around. And a calorimeter is really made to measure heat exchanges and help calculate those constants that we talked about, to calculate C, the specific heat of a material. So, well, as I said, you can either heat a sample up and drop it in, or you can look at the equilibrium temperature afterwards. You can see how much the temperature increased, or you can sit there until it goes into equilibrium, and then you can figure out how much thermal energy left your sample. So in calorimetry, we assume that no mass enters or leaves and only energy is exchanged between the materials. So if a block of ice melts, we don't worry about the increased mass, how much mass of ice was added to, say, our liquid. All we care about is how much energy flowed from the ice to the liquid. So open system, we don't worry about mass transfer. Isolated system in terms of energy, though, is very important. We say we have this isolated system. That's what that styrofoam container around the outside of our glass jar, our glass beaker, was really doing, was making a closed system where we don't worry about losing energy to the environment, to the atmosphere, and all we care about is the heat lost from whatever material we introduce into the fluid in the beaker. So in an isolated system, energy out of one part equals energy into another part. Heat lost from one material equals heat gained by the other. A statement of the conservation of energy. So quite often, figuring out the C value, the specific heat of an object, is what you want to do. So let's take a look at an example. Here we have a 0.5 kilogram block of metal with an initial temperature of 54.5 degrees C. And it's dropped into a container that is holding 1.1 kilograms of water at 20 Celsius. The final temperature of the block water system, so once it's equilibrated, the final temperature becomes 21.4 Celsius. What's the specific heat of the metal? What's the C value of this metal after this has happened? So we put our hot metal into the water. It increases the temperature of the water from 20 Celsius to 21.4. We want to find out what C is. Let's assume the container can be ignored, so there's no exchange of heat with the surroundings or the container itself. So there's the kind of system we're talking about. Here's our container, our perfect insulator. We throw this metal in here, and this metal is hot. There's a lot of Q in here. That heat energy, that thermal energy, is going to flow out of the metal, down the gradient, into the colder water, and heat up the cold water. That will cool the metal and heat the water. This will then, as we say, increase the temperature of the water to some value and give us a delta T for the system. So we cared about the specific heat of the metal. What was C? So we want to write out an expression for the heat flow out of the block. The Q of the block is negative because the temperature is less than the overall temperature of the block. So Q block equals M mass of the block times the specific heat of the block times the temperature of the system minus the temperature of the block. Now, let's write an expression for heat flow into the water. So we've gone from the perspective of the block. Now we're going for the perspective of the water. So Q for the water is going to be positive, since the temperature, the final temperature here, is greater than the initial temperature of the water. So Q for the water, same statement, Q equals mc delta T. Here's mass of the water, C for the water, T minus TW. So, by conservation of energy, we can set the sum of all these heats to 0. We said the values were negative for the block, positive for the water. So Q block plus Q water should equal 0. And this is just substituting in the expressions we stated in the previous slides. Mass of the block, specific heat of the block, delta T block, plus mass of the water, specific heat of water, delta T for the water. This should really say TW. So now let's solve for CB, the specific heat of the block. And that's what we care about, the specific heat of the block of metal. If we rearrange our previous equation, we'll end up with mass of the water, specific heat of the water, times delta T over mass of the block times delta TB. Substitute the values in. Now, I've switched the temperatures around here and done this from the water's perspective. So by switching my delta T around, we can find out how much energy really flows into that system. So what we'll end up with is a magnitude that we care about of what is the specific heat of the block. This just makes the numbers work in this particular case and looks at this from the water's perspective and gives us a value of 390 joules per kilogram Kelvin, which probably makes this something like iron or steel. So this is something you can do here if you're talking about where is the energy flowing from and to. Here it's flowing from the block into the water. So I switched these around in order to express that from that perspective.